When carrying out a study, if we observe an interesting relationship between two variables, and we've concluded that it doesn't seem to be just due to chance, we might want to ask the question, does changing one of the variables cause the other variable to change? In this video, we'll begin to investigate whether or not we can answer that question. Here's a headline that concerned those of us who love eggs. Can they really be as great of a cause of heart disease as smoking is? Or maybe it's possible that people who eat a lot of eggs also tend to eat a lot of fatty foods, and so there are other dietary factors that contribute to heart disease rather than the eggs. Another recent headline reported on the negative effect on IQ of teenagers smoking marijuana. But maybe it says more about who smokes marijuana than the actual effects of the marijuana. For example, socioeconomic status has been blamed as a potential alternate factor contributing to the drop in IQ. If we want to be able to make causal conclusions about one variable causing another, we need to control how the data were collected. Let's start with a general paradigm for our study. For simplicity, we'll assume that we're interested in comparing just two groups, and these two groups are in two different situations. There is a particular variable called the response variable, or outcome, that we're interested in comparing between the groups. This could be cardiovascular disease risk, depending on whether or not one eats egg yolks, or IQ in pot smokers and non-pot smokers, or error in age estimation between males and females, or life expectancy across two geographic regions, or infection rates for a vaccinated versus a non-vaccinated group. An explanatory variable is any variable that might explain differences that we observe in the response between the groups. An important concern when planning a study and analyzing the resulting data is the possibility of confounding variables. Confounding variables affect the response and have different values in the different groups we're comparing, so that it is impossible to tell if differences between the groups are due to the group composition or due to the confounding variables. To avoid having confounding, again, we need to collect the data carefully. Here are some ways we could collect some data. We often hear anecdotes about how a change in diet or environment has resulted in miraculous improvements to an acquaintance's health. For example, a close family member of mine eliminated gluten from his diet, and subsequently he lost weight. So, should all of us looking to lose a few pounds eliminate gluten? Not based on the strength of the evidence provided by this anecdote. It's a story about only one person, and I can tell you that this person happens to drink a lot of coffee, and he's had to avoid all the pastries in the coffee shop since giving up gluten. So we can't make any general conclusions based on an anecdote. Two other and better methods of data collection are observational studies and experiments. The advantage of an experiment over an observational study is the strength of the causal conclusions we can make. I've ordered these methods of data collection from worst to best in terms of the strength of the conclusions. We'll talk about experiments in more detail in another video and focus on observational studies for the rest of this one. In observational studies, as the name implies, the data are measurements of existing characteristics of a group or groups of individuals. The goal is typically to make conclusions about a population based on the sample of individuals we've observed, or to compare a measurement on individuals between different groups. Because existing characteristics are being observed, the investigator has no control over which group an individual belongs to. In contrast, in an experiment, the investigator imposes some kind of intervention on the individuals being studied, perhaps assigning some to one group and some to another. Experiments are the gold standard for making causal conclusions, but for now, we'll focus more on potential issues with observational studies. Let's look at an example of an observational study and discuss why we need to be careful when stating the conclusions of the study. The study we'll consider was published in the New England Journal of Medicine in May 2012. It was about the relationship between coffee drinking and mortality. Headlines in the New York Times and the Toronto Star reported that coffee may help us live longer. The Washington Post, in contrast, was a little more reserved. So, should we be pausing now for a coffee break? Here are a few details about the study. In 1995, the researchers collected data on over 400,000 men and women aged 50 to 71 and then followed them until 2008. By then, over 52,000 of them had died. They asked the question, did the amount of coffee these people drank affect how much longer they lived? The study is an example of an observational study. Subjects weren't told how much coffee to drink, they just did what they would do otherwise. In all observational studies, we have to be careful about interpreting our observed associations. Here, our explanatory variable is the amount of coffee drank, and the outcome is how much longer the subjects lived. Suppose the coffee drinkers tended to live longer, so there's a positive association. It may be tempting to say coffee causes long life, but there are other possible reasons why an association between coffee and longevity may have been observed. In observational studies, there are at least 5 mechanisms that could result in an observed association between the outcome and the explanatory variable. What we'd usually like to show is that changes in the explanatory variable cause the outcome to change. However, sometimes the outcome causes the explanatory variable to change. This is known as reverse causation. In our coffee study, maybe people with chronic health conditions who are more likely to die tend to purposely avoid coffee. It's also possible that the relationship is just coincidence. Another possibility is that both the outcome and the explanatory variable result from a common cause. Then the observed association is not because the explanatory variable causes the outcome to change, but because the common cause causes both to change. Whether a subject had diabetes is a possible common cause for the coffee study. Perhaps because of dietary restrictions, diabetics drink less coffee, and diabetics also tend to have shorter lives. And finally, there could be confounding variables. Confounding variables vary with the explanatory variable, so we don't know if we can attribute changes in the outcome to the explanatory variable or to the confounding variable. One of the many possible confounders in the coffee study was smoking. Smokers tend to drink more coffee, so smoking status is associated with our explanatory variable. And smoking also has a causal effect on our outcome, length of life. We can't fully understand the effect of coffee on length of life unless we adjust for smoking. Imagine if a study showed that coffee drinking was associated with shorter lives. Could we blame it on the coffee or the associated smoking? In observational studies, even when we observe an association, we can't conclude that the explanatory variable has a causal relationship with the outcome. There are at least 5 mechanisms that can result in the association. As we saw in a previous video, in the example with Simpson's paradox, there are also variables that can be lurking, sometimes also called hidden variables. A lurking variable is a variable that is not accounted for in the analysis, but it affects the association being considered. In the previous video, we saw the effect of age, which was associated with mortality, our response, and also with smoking, our explanatory variable. And when age was considered in the analysis, it reversed the nature of the association between smoking and mortality. Lurking variables can be confounding variables, as in this smoking, age, and death example. They can also be the source of a common response, or just another variable that, if we had considered it, it would change the nature of the relationship we're looking at. In the coffee study, method of preparation is a possible lurking variable. We can't say if differences in the composition of espresso versus filtered coffee affect the protective effects of coffee, and thus would influence the relationship between coffee drinking and length of life. Controlling for confounding variables is a difficult part of the analysis of any statistical study. In another video, we'll talk about the use of experiments to mitigate the possibility of confounders.